Welcome back. This is Innk, and in today's problem, we're going to use nodal analysis to find the current Ix. As always, we pick a terminal that connects the most branches and apply KCL at that point and call the equations we generate at that point a node equation because it's a node. In this case, we want to find Ix, so we can choose the terminal above Ix. We can call that V1, but note that we have some voltage sources in the circuit causing there to be voltages at these 2 points. We would want to know those voltages in order to know the voltage above Ix. So we can start from the left and say this is V1. Above Ix, that's V2, and we can call that V3. Put our ground because we take voltage with reference to ground if there's no voltage source, and we call ground 0. So first up, we can first start with V1, and that's our node equation. We can generate our equation. We can take V1 with reference to the 2-volt source. That's on the right. That's on the left side of the circuit, the first branch, or the lower left side of the circuit. Let's call it that. So V1 with reference to the 2-volt source. In this case, we are seeing the positive terminal of the voltage source. So that's a positive 2. So V1 minus a positive 2 all over 0.1 plus V1 with reference to V2. So we subtract V2 from V1, and that's all over the 0.5 ohms resistor plus, in this case, V1. So now we're dealing with the top branch of the circuit. So we take V1 with reference to V3. So that's V1 minus V3. Then notice we have a voltage source within that branch that we took the voltage across. So if we want to know the voltage across that branch, we are looking at the positive side of the 4-volt source. So we would say minus 4 volts. So minus 4 volts, because minus a positive 4 all over 0.2 ohms, and that's the resistor within that branch, and that's equal to 0. Simplification leads to V1 over 1 over 0.1 plus 1 over 0.5 plus 1 all over 0.2 plus V2, and V2 is negative 1 over 0.5, and that's plus V3, and V3 is negative 1 over 0.2. Pulling out the constants, we see that there's a negative 2 all over 0.1, a negative 4 all over 0.2, that is equal to 0. Simplification leads to V1 being with a constant of 17, V2 with a negative 2, plus V3 with a negative 5. And that's equal to 40. These constants simplifies to negative 40. We move the 40 over the right-hand side. Let's call this equation A. Moving on to terminal V2. We take V2 with reference to V1. So that's V2 minus V1 all over 0.5 plus V2 all over 0.1, because that's V2 with reference to ground. So ground is 0 volts. So V2 minus 0 volts is V2 and all over 0.1 plus V2 with reference to V3 all over 0.5, and that's equal to 0. Simplification of these, I'll skip the step of factoring out and just go straight to the simplification. We'll call that equation B, and V1 is going to equal negative 2 plus V2 is going to equal a 14, a constant of 14, plus V3 is a negative 2, all equal to 0. That's equation B. We move to terminal 3, applying KCL at that terminal. First, we take V3 with reference to V1, and we're still dealing with the top branch with the 4-volt source between that branch. So we take V3 with reference to V1, Notice that from V3, we're seeing the negative side of the 4-volt source. So V3 minus, so in this case, you say minus a -4, which will give you a +4. So in this case, plus a +4 all over 0.2 ohms. Plus V3 with reference to V2. All over 0.5 ohms plus V3 with reference to the 3-volt source on the lower right of the circuit. That is 3 volts all over 0.1 ohms. That's equal to 0. Simplification leads to equation C. And that's V1, -5 plus V2, -2 plus V3, 17, equal 10. So in this part of the problem, we notice that we apply KCL at all 3 terminals and we generate the node equations for all 3 terminals. Simplification of each, we get equation A, B, and C. We factor out all the variables and we could just put them into a calculator and punch out the needed values. So simplification followed by simultaneous solution leads to V1, V2, and V3. In this case, V1 is equal to 2.865 ohm, 2.865 volts. V2 is 0.625. So 0.625 volts. V3 is 1.51 volts. And to find Ix, we want to know the voltage across the 0.1 ohms resistor. And that's the voltage at terminal V2, all divided. So now to find the current, we use the voltage at V2 divided by the resistor. So Ix is now equal to the voltage at terminal V2, all divided by the 0.1 ohms resistor. And the current in this case would be 6.25 amperes. That's it. See you in the next problem. Thank you. Bye.